Good morning all to all the children of grade 9. This is the continuation of work and energy, chapter number 11. So, in the previous class, you have learnt about the definition of work, units of work, when the work is done, whether the work is positive, negative, or zero. Today, you will learn about energy and power. As we have already discussed, that we need to do a lot of work, and for doing work, we need strength. And that strength comes from the food we eat. For example, if you need to ride a bicycle, you need to paddle it, and for paddling, you need to do work, and for it, you need strength, which comes from food. Strength here refers to energy. So we can define energy as the capacity to do work, or energy is the ability to do work. I repeat, the capacity to do work or the ability to do work is called energy. It is a scalar quantity and it depends upon work. Therefore, its unit is the same as that of work, that is joule. What are the types of energy? Energy is of different types, like a machine produces mechanical energy, the heating device produces heat energy, like bulb, etc., produce light energy. So we actually come across a different forms of energy. The common form that we are going to consider here is mechanical energy. Let us check out. Let us check it out. Mechanical energy is it is the energy possessed by a body due to its position or motion. I repeat, mechanical energy is the energy possessed by the body due to its position and motion. Remember, position and motion. Suppose you notice a book lying on a table. Do you think it possesses any kind of energy? Yes, it does. And that is the energy due to its position called potential energy. Likewise, how can you say that a book lying on the table possesses potential energy? You imagine there is no table in a second and the book falls down on its own. Likewise, if we notice a girl riding a bicycle or a car moving on the road, they all are moving, so they possess energy due to motion, that is kinetic energy. So let us see what is mechanical energy, the sum of potential energy and kinetic energy. Types of mechanical energy, that is potential energy and kinetic energy. We can define both as the first one, potential energy. It is the energy possessed by the body by the virtue of its position. It is given by the following relation: PE is equal to mgh. Please note, all bodies are objects possessing potential energy due to their position. The three types of potential energies are gravitational potential energy, chemical potential energy, and elastic potential energy. Gravitational potential energy. Energy potential that comes from the objects at certain height and due to weight. Chemical energy is energy potential coming from the atoms it contains and the chemical reactions that take place within the object. Elastic energy, energy potential on object being compressed or stretched, like a spring. You press the spring and leave it like that. Press the spring, immediately when you release the weight, it goes to its original size. Whereas a stretched rubber band, as long as it is stretched, and it is always trying to contract as soon as you release it. Even a bow, you stretch arrow in the bow, a stretched arrow in the bow is also having potential energy. Let us come back to the screen. The potential energy of an object at a height. When an object is raised to a certain height, work is done against gravity to change its position. This energy is stored as potential energy. We already know what is work. Work is force into displacement. And from second law of motion, we know Newton's second law of motion, F is equal to ma. In the case of increasing the height, F is equal to mg. Instead of ma, force is equal to mass into acceleration. We can change mass as mass is constant anywhere in this universe, m remains as m. A changes to gravitational force because when a body is at certain height, it is under the action of gravitational force. Therefore, work done, that is potential energy, is equal to mass into acceleration due to gravity into height. So substituting the value of F is equal to mg in the equation W is equal to F into S. In W is equal to F into S, you are going to substitute F is equal to mg. Then you will get F is equal to mg S. S is nothing but displacement. Displacement is nothing but the height here. So PE is equal to mgh, and it has the same unit as that of work, that is joule. Let us get into kinetic energy. It is the energy possessed by a body by the virtue of its motion. Example, a speeding train, flowing water, etc. Here you can see the difference between potential energy and kinetic energy in the pictures. So a ball which is at rest at certain height is having potential energy. Potential energy is transferring into kinetic energy when the ball is in motion. So when it is falling down. How to derive expression for kinetic energy? Objects in motion possess energy and can do work. This energy is called kinetic energy. We know double F is equal to ma according to Newton's second law of motion. Also, from the first definition of this chapter, work done is equal to force into displacement. So, we know from third equation or second equation of motion, v square minus u square is 2as in equations of motion. From our laws of motion or equations of motion, we get s from v square minus u square is equal to 2as. Make s as subject. When you make s as subject, you get s is equal to v square minus u square by 2a. So substituting this s value in the w is equal to f into s, what do we get? W is equal to ma. Ma is nothing but force. F is equal to ma. So in place of F we write ma, and in place of s we write v square minus u square by 2a. Then if you remove a in the denominator and a beside m, then m into v square by 2 you will get. If the initial velocity, that is u, is 0, then u square becomes 0 and only v square remains in the bracket. So mv square by 2, which is nothing but half mv square. This is how we get kinetic energy. Ke is equal to half mv square. Law of conservation of energy. According to it, energy can't be created or be destroyed, but can be converted from one form to another. But the total energy of a system remains constant. Suppose a ball is lying at a height. We know that due to position, it possesses potential energy. Now, due to any reason, it falls down, so its potential energy gets converted into kinetic energy. It has been observed that the total energy remains the same, only the form of energy changes, that is either potential energy or kinetic energy or both. Explanation. A theoretical explanation or example to illustrate the law of conservation of energy. Consider a body of mass m at a height right of, that is at a height, that is not right, at a height of h held by a person. Let the body be released such that it falls freely under the acceleration due to gravity g. Let us consider the total energy possessed by the body at the height h from the ground level and at the ground level. So let v be the final velocity of the body on reaching the ground level. When the body is at a height of h from the ground level, as the body is stationary, its velocity is 0 and it is having only potential energy and its kinetic energy is 0. So potential energy becomes mechanical energy, then total energy of the body is potential energy plus kinetic energy, that is mgh plus 0. Only mgh is there for a body which is at rest at certain height. In case 2, when the body just reaches ground level and its height is 0, let us calculate the velocity of the freely falling body at a ground level. So v square minus v square is equal to u square plus 2gh, or v square minus u square is 2gh. In place of as, we write g and h. As initially the body is at rest, therefore u square is 0, then v square is equal to 2gh. So kinetic energy is half mv square, that is half m into, so v square is nothing but 2gh. We write 2gh and it is equal to mgh. So kinetic energy becomes mgh. That is nothing but energy is mgh. So potential energy mgh is equal to m into g into 0, that is 0. So total energy of the body again is potential energy plus kinetic energy is 0 plus mgh. It remains as mgh. As the total energy of the body remains the same, the law of conservation of energy stands proved. Only energy changes its form from potential energy to kinetic energy or vice versa. What are the examples of conservation of energy? Examples of transformation of energy are as follows. When hands are rubbed, the mechanical energy of hands changes into heat energy due to friction. When two stones are stuck, the mechanical energy changes into heat energy and sound energy due to friction. When the blade of a knife is placed against the rotating grinding stone, the mechanical energy changes into heat and light and sound energies. When the brakes are applied on any moving vehicle, the mechanical energy changes into heat energy as the brakes rub against the moving wheels. When we wind a watch, the mechanical energy of hands change into potential energy of the spring. When the spring unwinds, the potential energy changes into kinetic energy and drives the hands of the clock. When an arrow is stretched in a bow, the mechanical energy changes into potential energy. On releasing the string of the bow, the potential energy changes into kinetic energy of the arrow. Water stored in a hydroelectric dams has potential energy because the position of the water is there at a certain height. When this water is released, the potential energy changes into kinetic energy of the flowing water. The kinetic energy of the flowing water turns the blades of a turbine and drives the dynamo. The dynamo then produces electrical energy. When a torch is switched on, the chemical energy of the cell changes into electrical energy. The electrical energy on passing through the filament of the bulb changes into heat energy and light energy. In an electromagnet, electrical energy changes into magnetic energy. The electrical energy on flowing through the coils of an electric motor or an electric fan changes into mechanical energy. It partly changes into heat energy and hence heat hits the coils. In another example, in microphone, the sound energy changes into electrical energy. Electrical energy on flowing through the speaker of an audio system changes into sound energy. Next point, in electric heaters, electric ovens, and geysers, the electrical energy changes into heat energy. In a locomotive, the chemical energy of coal changes into heat energy. The heat energy then changes into kinetic energy of steam, which drives the locomotive. In the next example, 15th one, in an electric generator, the mechanical energy changes into electrical energy. Example 16, in a photovoltaic cell, the light energy changes into electrical energy. Example 17, in television, the electrical energy changes into light energy and sound energy. Example 18, on burning the fuels, their energy changes into heat energy and light energy. When a matchstick is rubbed against the side of a matchbox, the chemical energy changes into heat energy and light energy. When a cracker is exploded, the chemical energy stored in the chemical uses used in the cracker changes into heat, light, and sound energies. During photosynthesis, light energy changes into chemical energy in the presence of chlorophyll. During respiration, the chemical energy of food changes into heat energy. It is the heat energy which keeps our bodies warm. It is also the heat energy which changes into mechanical energy during locomotion. During charging of a battery, the electrical energy changes into chemical energy. During nuclear fission or fusion, it is the nuclear energy which ultimately changes into heat energy and light energy. So these are some of the examples of transformation of one form of energy into another form of energy. Let us come to the last part of this chapter. What is power and what are its units? You must have noticed that whenever we buy a bulb or any electrical appliances, we ask for how many watts of power it is consuming. This reading is power. All the electrical appliances possess certain power which actually shows how much energy will it consume in a given time. We see not only bulb, we see ceiling fan, which consumes 70 watts. So 70 watts per hour, or so it is having 70 watts consumption. So when it consumes total of 1000 watts, then 1000 watts is 1 unit in our current bill. So let us go through clearly. Power is defined as the rate of doing work. I repeat, the rate of doing work is called power. Power is a scalar quantity. So from this chapter you have to learn that work work is a work SI unit of work is joule. It is a scalar quantity. Energy is a scalar quantity. So power is a scalar quantity. Now let us go through what is watt. Unit of power is called watt. WATT. 1 watt is 1 joule per second. 1 joule is the unit of work and 1 second is the unit of time. So when 1 joule of work is done in 1 second, then the power is said to be 1 watt. Bigger units of power are gigawatt is nothing but 10 power 9 watts. Megawatt is 10 power 6 watts. Older unit is horsepower. 1 horsepower is 746 watts. If we need to calculate electrical energy consumed by electrical appliances, we can calculate by E is equal to N into P into T. Energy, when N specifies the same kind of appliance with same power and same working hours, then commercial unit of energy is kilowatt hour. K is nothing but, in modern days now, at present we are saying kilo is nothing but 1000. So even for 1000 rupees we say 1k rupees. In such a way K is used. So kilowatt hour. You must have seen your home electricity bill, and the bill that we get is like 45 units, 100 units, 700 units. Those who have even AC is being used at this time, you get 400, 500 units utilized. Get your power bill, and that is electricity bill, and watch, just observe how many units of power you have consumed in the past 1 month. So those units are actually kilowatt hour. 1 kilowatt hour is 1 unit. We can also relate kilowatt hour with joule as follows. 1 kilowatt hour is 3.6 into 10 power 6 joules, or 3.6 megajoules. 1 kilowatt hour is the unit of electricity. So once again I repeat, 1 kilowatt hour is 3.6 into 10 power 6 joules or 3.6 megajoules. 1 kilowatt hour is the unit of electricity. What is the unit of electricity? 1 kilowatt hour. What is the unit of power? Watt. What quantities are work, energy and power? They are scalar quantities. So with this we conclude this chapter, work and energy. Thank you.